So this is the simplest possible. So if I can find the simplest possible logic expression that guarantees number one design requirement, that you must implement the circuit using the minimum possible number of transistors. Design requirement number 2. In the circuit there cannot be a path with more than 4 transistors in series. That means in the final logic expression you want to make sure that there is no AND or NAND term with 4 variables. If you have a term like this, let's say like A, B, C, E, it's a 4 series in transistor. So we want to make the circuit efficient, so we want to minimize the length of series transistor. In this given problem, I gave you a restriction that your circuit cannot have any series path with 4 or more series transistors. So you cannot have any AND or NAND term with 4. It has to be 3 or less, right? So you have to keep simple, like I start with all 4. So with that design restriction, so none of this, so 1, 2, 3, 4, 5 of the terms here with 4 variables. So you cannot have any, so you have to minimize them. These are because we want to basically ensure this certain performance. Now that we have the simplest expression, let's say now we want to implement CMOS, static CMOS version of this circuit. Now I actually put a third requirement restriction. The input signal associated with D is the most active, A is the least active. So we know that from one of the design technique we have discussed in lecture 4, the most active signal should be placed close to the output, not closer to the supply of ground. So the most active signal should be the closest to the output, not to the source and gate. Now, B and C with A and D. So in the NMOS network, let's first draw the NMOS network for this circuit, right? B plus BC plus B. So now, let's say this is my output line. Capacitance CL. Now in the NMOS network, there are 2 parallel paths. One parallel path will be comprised of 2 series transistors. We will assign that will be BC, right? The other parallel transistor, other parallel path ADE, one option is I put A here in series parallel, D and E here. This is option number 1 and this is B and C, right? B and C, they are in series and there is nothing mentioned in the problem that whether between B and C, which one is more active. So you can put B here or B here in any way you want. But the question says the input signal D associated with D is the most active. So the D should be closer to the output, right? So please, those who came late, get one from here. These are some examples we are talking about. So logically, the way I drew it here, it is correct, right? Because A is in series with B plus E, right? Logically, the circuit is correct. But the actual circuit which I want you to implement, D is the most active, and so actually D, this whole block, D should be closer to output. That means this one, so actual circuit should be, let's draw it here. This is my output. This is CL. B and C in series. As I said, in series you can put B here, C here, or C here, B here, it doesn't matter because there is, but here I should put this is D and this is E in parallel, in series with A. So this is the, for this given, logically this one is correct and this one is correct. Both are exactly same. For the given constraint, D being the most active signal must be closer to the output. Right? So now, after drawing this pull down network, this is my pull down network for this. Right? So, then now, I'm creating some space. So let me draw it here. D, E, A. B and C. So this is my pull down network. For static CMOS, the pull up network will be coming from here. B and C together will be in series with ADE, right? So now, now the question is, so B and C, this block will be in series with ADE block in pull-up network. But D being the most active, this block should be closer to the output. So I have to put here the block containing ADE. So now here, A is in series with DE. So here, A should be in parallel to D and E. D and E are in parallel here. So they should be in series here. This is single A. Now the question is, in this series D, so D and E are parallel here, D and E should be series here. So between D and E, which one we will assign here?
D.
D, because it is most active. So you're getting there. So they are in parallel. Why? Because A is in series with block D. Now B and C is in series here. So I have to have another block here between VDD where I will have this situation. B, P. Make sure that these are all PMOS. These are all PMOS. Right? These are all PMOS. So this is B, this is C. So that is basically the, you can draw any way you want. This can be a middle line. Just one line. I can make it like a simple. Simple. Just one line. This is B. Just to make it look good. So this is C. So this is B, this is, and then I can make one ground line just to make the circuit simpler. This is ground. So now this is the static CMOS. So now if you want to implement N-type dynamic, what we will have? We will have pull down. So this one, we will have a clock transistor here, NMOS clock connected to ground. And then here, there will be no pull-up network. There will be a PMOS clock transistor here. right? With VDD, this is N-type dynamic, right? So this is N-type dynamic, everything remains same. And then what about P-type dynamic? P-type dynamic is basically, so there will be a clock transistor here, and then my pull-up network is basically A in series with D and E, right? This is A, this is B, this is C, this is E, this is D. All PMOS, B, C, right? A, B, D. So this is my output. This is load capacitance. From here, there will be an NMOS clock transistor, right? This is VDD. So this is my P-type dynamic. This is complete static CMOS, right? So P-type dynamic for the same function, N-type dynamic and static CMOS. So condition number 1, 2, 3, we satisfied in all of them, making sure that we first come up with the minimum possible expression so that minimum number of transistors can be used. We break down the large, basically terms into smaller terms using Boolean algebra so that we don't have any term containing 4 or more. Everything has to be 3 or less. So you have to keep simplifying the logic function if that is the restriction. And then input D is the most active. So for any permutation and combination, we have to make sure that D remains closest to the output in the pull-up and pull-down network. So now, if I want resistive load ratio design, then it will be, there is no clock here, it will be connected to ground because it's like CMOS pull down. Here just a single resistance, that's it. That is the resistive load ratio device, right? Now if you're done with it, now let's do another ratio device, pseudo and MOS ratio device, right? Pseudo and MOS ratio device. The only thing is, it is no longer resistance, it's a PMOS transistor which is permanently grounded, so it is always on, right? So all you need to, first step, simplify the logic function, get the pull-down network for CMOS, then complementary pull-up network, you get the static CMOS, this one delete, you put clock signal for dynamic, no clock signal in ratio logic. So you have actually now 1, 2, 3, 4, 5, 6, and DCBSL is, you implement this one, pull-down network. I'm not showing here. You draw a parallel pull-up network. This series becomes parallel here. This parallel becomes series here. On the top, there will be 2 PMOS, but they will be cross-connected. This one will be connected to this output. This one will be connected to this output. So just, you can do. The second example, I want you to do practice at home, but let's talk about few other things here. What are the design problems you have to solve? Example 2, I want you to practice at home. Now the example 3. Example 3, actually, a function that is given. So by the way, in all of this circuit, it says F equal to this. But what actually we are getting here?
F bar.
F bar. So make sure that you put an inverter, then write F here. Very careful. Because in every implementation from static CMOS to PWM dynamic to stereo CMOS, every implementation, direct implementation is giving us F bar. So there is a reason why I put problem number 3. So F is equal to ABC. So for whatever reason I use a small letter. So this is whole bar, right? So now, for the time being, let's forget about this. So this is all, actually there is another way to write this. If F equal to this whole bar, it is exactly same as writing F bar equal to ABC plus AB prime C, right? That's what it is. So now, this is what I have to implement. So if I implement this one directly, I am getting F bar, right? Implementing F equal to this expression whole bar is same as implementing F bar uninverted here. Now, can we simplify this?
Oh, I think you also have a bar of the B, you have a bar of the B and C.
Oh, well, I actually base the whole bar. I actually, yeah. So base the whole bar. Can we simplify it? If I take A common, this is a trick question. First, so here, so BC plus BC bar is what? 1. So you don't have to implement anything. So
You gonna put that one on the test?
huh?
You gonna put that one on the test?
No, I just
Extra credit.
no, it just to show you that if you come to this type of situation, then it is a buffer. Buffer means whatever you signal, you apply the input, you will get the output. It's a buffer. It's not even an inverter, right? But it's actually an inverter. It's actually an inverter. F bar equal to A. So it's basically what you are going to do is, this is F, this is F bar, right? Or A. So it's an inverter. So, but in your exam you have to solve a real problem like this. Now, for example, like I condition for T, internal node capacitance cannot be ignored. So your first task in this case is to identify the nodes that will have internal node capacitance. So design requirements or restriction number D is internal node capacitance cannot be ignored. Identify nodes. Now VDD is supplied, so this line or this node, no internal capacitance. This is a candidate node because this is a common node for this one, this one, this one, this one. So there has to be an internal node capacitance here. Now this output node is connection of so many different. Now let's come to this way. This way, well, this is an internal node. Now look at the other side of A. Other side of A is connected to output, so it is already included in the load capacitance. Now let us follow this part. Follow every part. This node above E is whatever capacitance it is contributing, it is included to this internal node. But between E and D there is a node here. It is an independent circuit node, not common to anything. So I have to put another internal node capacitance here between D and E because it's a separate. But the lower end of the D is connected with the output. So all the capacitance contributed by A, D and all this will be included in the load capacitance. Now let us look at the pull down part. I will always start from ground up. Let us follow this part. This is an independent node, right? So I will have an internal node capacitance here. This included in the load. Let us follow this part. This will have an internal node capacitance. This node will not have because it is included in the load capacitance. So I have 1, 2, 3, 4. So that will be one of the tasks basically in the exam or problem. Identify the nodes that will have internal node capacitance and put an internal node capacitance in the equivalent circuit. So the next step is, if I want you to draw the equivalent circuit for this whole CMOS implementation. What is equivalent circuit? The equivalent circuit for will be here VDD. Then I will have a resistance with the switch, right? And then here I will have a resistance with the switch for BC. They are connected. This node will have an internal node capacitance, right? And then from here I will have a resistance with the switch for, this is BP, BPMOS, CPMOS, this is APMOS, and D&E in series, right? So let's draw it from here. So D and E, one switch, another switch. This is just the equivalent circuit for PMOS network. So this is E of P, this is D of P, and then in between this node, I have to draw another internal node capacitance, right? So now you have to draw, in the similar way, you have to draw the equivalent circuit for the entire NMOS network. Because we need to identify the resistance capacitances for the given input combination. So now, and I put another restriction that the circuit must be symmetrical for the worst case low to high and high to low transition. And you have to use uniform sizing, and also another, to make it simple, all the internal node capacitance are equal. So you have to solve this type of problem in your actual question, you have to have the number or the value. What is that internal node capacitance? That should be given to you. And the worst case symmetry, that it should be symmetrical, that means propagation delay should be equal in the worst case, that is the symmetry. And you have to use uniform sizing. So probably you need RN naught information, RP naught information. What is the resistance of unit size NMOS resistance and unit size PMOS resistance to test the condition, right? To test what is the condition for symmetry? Kn should be equal to Kp. So now all Rn equivalent equal to Rp equivalent. That is the condition for symmetry. But first, we have to identify for this given circuit what input combination will give you worst case low to high and worst case high to low. Now we are going to explain something which we did not explain in lecture 4. So you can say it is a continuation of lecture 4. You will see that worst case scenario must consider lot more factor than what we have discussed in lecture 4. So now, first option. Worst case means for high transition, identify the longest path from output to the ground or output to supply. So for high to low transition, I have one path comprising B and C, 2 transistor. I have another part comprising D and A, 2 transistor. I have another part comprising E and A, 2 transistor. So, just looking at this, so I should not turn on more than one part in the worst case, right? In the worst case, only one part out of 3 possible parts should be on for high to low transition. So one option is BC equal 1, A, D and E equal 0. Option 1. Option 2, A and D equal 1, B, C and E equal 0. Option 3, all are 2 transistor part. A and E equal 1, B, C and D equal 0. So all 3 will have a high to low transition through 2 transistors. That is the longest possible path. But now we have to see for any of this combination, are we getting disturbed by any of this? Any path from here. So when I'm making a high to low transition, what I'm doing? I'm discharging output to the ground. And also another interesting thing is that this option, and this option, in all 3 options, in the pull-down network, when I am discharging the output, I have to, if I follow this path, I have to take care of this internal node capacitance, discharge it. If I follow DA path, I have to discharge this. If I follow EA path, I also have to, that means in all 3 cases, I have to discharge output and one internal node capacitance. So it looks like there is the worst case scenario in this circuit. So we have to look at now on the pull up side for all 3 combinations. Now, let's say with B and C equal 1, AD equals 0. This option number 1. What happens in the pull-up side? With B and C 1, this PMOS is off, this PMOS is off. But with AD is 0, this is on, this is on, this is on. Right? So in my, now, since this is on, for this input combination, this transistor is on. So while I am discharging this capacitance and this capacitance to the ground, because this transistor is on, this capacitor is also connected to the ground, so it will also discharge. Because this is on and this is on, both of them are on parallelly, this internal node capacitance now is getting a path to discharge all the way to the ground. So for this input combination, I am supposed to discharge only one node capacitance and one internal node capacitance coming from this part. But now, because these 3 on, these 3 off, so there is no connection from output to the supply because they are off. So there I will not have a low to high transition. I will still have a high to low transition because and pull down path establish the connection from output to the ground, but these 3 will be slowing down this high to low transition because now I have to take this to extra internal node capacitance from the pull-up path. Pull-up path should not be disturbing high to low transition, but the way the circuit is designed, this will basically now what the scenario I will have for that input combination. The scenario now I have here is, this is my output, this is load capacitance. For ADE 0, this whole path is off, so I can discard it. So the equivalent circuit for that input combination I have is, because both B of n, C of n, and I have an internal node capacitance here, but from here to here, I have an internal node capacitance here, and then I have D and E in series on. All the switch will be on, and I have an internal node capacitance here, and then I have this. This is AP, this is DP, this is DP, right? So now as you can see, as I am discharging this, I have to discharge this, I have to discharge this, I have to discharge this to parallel path, right? So now the delay, the whole response will be much slower, high to low transition, because I have to take care of all this additional. So then I have to calculate tau. We have to find the equivalent circuit for their input combination. And for that, I have to calculate tau using Elmore relay constant. Starting from here, this resistance is discharging how many capacitors? 1, 2, 3, 4. This resistance is discharging how many capacitors? 1, 2, 3. This resistance will be discharging only this capacitance. This one will be discharging this one plus this one. This one will be discharging only this one. I can go by resistance or capacitance by capacitance. Get the tau? Yes.
There should be another C
Where that another
on the
C?
top.
Where C will come from?
There is a D and C. Oh yeah.
ED. So there is a common, then I put that capacitance here, right?
Yeah.
And then this is a common node for A, D and all this, so that is already there. Now for this input combination, now let's say combination number 2. Let's write with a different color. Combination number 2. AD1. So this is on, this is on, this is off, this is off, this is off, right? So now from output to the ground, I have a high to low transition path. But what happens for this input combination in pull-up path? BCE0. So this is B. So this is on. This is on. E0 means this is also on. A and D1. So this is off. This is off. In this particular case, although they are on and there are internal capacitance, because both sides, A side and D side, it is disconnecting this whole pull-up network from the output node. Nothing will disturb from pull-up side, right? So now, just use your common sense. Comparing 1 with 2, 2 will be much better option. It's not a worst case option, because it is, in this case, the high to low transition doesn't need to take care of anything from upper side. So this is not a worst case. Although initially we found out that 3 equal paths all contributing, all discharging CL and C internal in the pull down path. But now we ruled it out because this one will be much longer delay. Now let us look at option number 3. Option number 3. BCD0. Off. B, A and E1 on. From output to A and E, two transistor path, like, but with that here, what I have, B on, right? C also on, because it is D also on, right? D on. For this one will be off. A is 1, E is 1, this one is also off. Now as you can see, A is off, so nothing will come to this way contribution wise. These two are off, so this is out of question. But D is on in this case, right? So what I will have an equivalent circuit wise, for me it is easy to draw. So what I have now, a contribution, if D is on, these internal node capacitors now had a pathway to the ground. So here, this side I will have E on top, A below, right? E and A on. But here I have to make sure that D of P is on, and this is adding another internal node capacitance. So for this combination, I have to take care of one internal node capacitance, two internal node capacitance, and three internal node capacitance. So this is slower than this, but definitely this one added a lot more. So this one is the worst case, this one is the second, this one is the third. So this will be my worst case delay. So what is the conclusion? For any given input combination, first thing is, if there is only one longest path, you don't have to worry anything. If there are more than one path of equal length in pull-up or pull-down network, you look to the other side. For that given input combination, how many additional transistor and capacitor this input combination is connecting with the other side or from the pull-up network. So this is the worst case input combination. So you don't have to draw the equivalent circuit like this, but you see on your problem after drawing your circuit, for the given input combination, how many additional transistors are on and getting a connection to the output from the other side while you are taking care of high to low transition, or when you are taking care of the low to high transition, how many additional capacitor here need to be charged. So now for the same problem, this is for worst case high to low. Now for the same problem, let us now look at low to high transition. Let me delete all those. Let me delete all those. So for low to high, now I'm talking about worst case for TP, low to high. Here the problem is actually simple, because from VDD to output, one path is containing, this one is one possible path, right? This one is second possible path, right? This one is third, right? This one is fourth. Four possible path. Now, this one, the first one has 2, fourth one has 2. But number 2, this is B. B, E, D, 3, C, E, D, 3. So now, option 1, B equal E equal D equal 0. So these two will be on, and then A equal C will be 1. Option number 1, right? Option number 2, C, E, D equals 0, A, B equal 1, right? Now I have to do the same thing. So I have two paths of length 3. So now for each one of them, let's see what the transistors are on. So let's say for this one will be on V0, E will be on, D will be on the upper side. B, E, D will be on. This one will be off. This one will be off. But now let us look at what is happening in the Coulomb cell. With E and D, with D0, this one is off. Right? With E0, this one is also off. Nothing is coming from this part. So it doesn't matter whether it is on or off, right? Because these two are off, so this whole path is disconnected. For this, B equals 0, also turn off this. So in this combination, no contribution for pull-down network because all these are disconnected. Now let us look at this scenario with CED1. So this is on, this is on, this is on. So I have a path, but with CED0, what is happening here? This is off, this is off, this is off, right? So both of them are off, this path is discarded. But AB1, so this is on, this is on, right? This is on and off, it doesn't matter because it's disconnected. But now see, B is on. This internal node capacitor is now connected to the output. So here, for this, what I have VDD. CPMOS is on in series with, it is, see, this is EP in series with DP. This is my output. Now here there is a path with an internal node capacitance. This is what? It is B of NMOS, right? And then this one has an internal node capacitance. This one has an internal node capacitance, right? So now, in this case, whenever I am charging the output, when charging current comes here, something will go down, it will charge this as well, right? So, in this case, while I'm charging to make a low to high transition, I have to charge one extra internal node capacitance through this because of the, for given input combination, this turns on. So two of them are of equal length, but this one will experience more delay. So this is my worst case. So as you can see, one of the most tedious tasks is to find the input combination that will contribute to the longest or worst case delay. Yes.
So what I understood now, whenever we are finding low to high case, we have to make sure that total capacitance that is discharging is the minimum capacitance. However,
For the worst case, the maximum. When yeah. So for high to low transition,
yeah, high to low is
for
not-
high to low transition, in addition to discharging output and the capacitances of the pull down network, is there any other connection capacitance from the pull up network that is getting connected to the output? If they get connected to the output, then while you are discharging the output, you have to basically discharge those additional capacitance from pull-up network as well. Similarly, when you are making a low to high transition, you are only supposed to charge the output capacitance through the internal node capacitance of the pull-up network. But if any additional transistor turns on and their internal node capacitance gets connected to the output node, while you are charging the output node, you have to charge that additional capacitance from pull-down network as well. That will slow down. Like you have one water pipe, now you have to fill one extra bucket. Capacitance is a charge bucket. So that will slow down your low to high operation. Yes.
I had a question about why in the low to high transition, B equals E equals B equals 0. How is that not immediately withdrawn from consideration?
So for this given input combination, if B is 1, with one signal, this NMOS transistor will be on.
No, the one above that.
The one above that.
Because B and E and
B and B, E, D.
But on the NMOS side of things, all of the transistors are off. So no capacitance can be pulled from the...
Yeah, that's why I ruled it out. That's why it is the worst case. I ruled it out. So this is the worst case. Because you are absolutely right. With this combination, no capacitor from pull down side will get connected to the output. So that's why it is not the worst case. This is the worst case because it is adding this extra transistor. So the summary is the input combination for both high to and low to high transition, the input combination in any direction that needs to take care of the maximum number of capacitance charging and discharging should be the one considered as the worst case. Because binary signal operation is nothing but charging and discharging capacitance at the output node. But while you are charging and discharging the output node capacitance, what additional parasitic capacitance you have to charge and discharge that will slow down the operation. So, I want you to do this step by step. Now once you know the equivalent circuit, the worst case, and then plug it into your propagation delay. So let's say you get your tau n and tau p for the worst case, right? So your TP worst case TPHL will be 0.69 tau n. Your worst case TPLH will be 0.69 tau p. So now, if you want to make them symmetrical, you have to make them symmetrical, then these two should be equal. So now, that means tau n and tau p should be equal for both worst case, right? Tau n and tau p should be equal. That means Rn equivalent times CL, Rp equivalent CL should be equal to Rn equivalent CL, right? So if I cancel this CL, that means my Rn equivalent should be equal to Rp equivalent, right? So what does it mean? It means that my Rn naught divided by W over L of equivalent should be equal to Rp naught W over L of P equivalent, right? If this value are given to you, so you know exactly what should be the equivalent size for this, right? If you know that equivalent size, if you know that total equivalent size for this, in this case, the worst case, there are 1, 2, 3 transistors in series. So you can distribute the size in uniform size All of them should be of equal size in the series part. But it is not that as simple, because that equivalent inverter or equivalent size distribution can be done only when there is no internal load capacitance. So in this particular case, if the internal load capacitance need to be considered, I will not ask you to calculate each individual transistor size, because that particular slide where we are showing series parallel combination of transistor, that formula is valid only when internal load capacitances can be ignored. Because if there is an internal load capacitance, you cannot merge them together. It's not like a simple. If you have three simple resistance or three simple transistor are in series without any internal load capacitance, you can merge them. But if there is an internal load capacity, you can. So that's why I will probably, as you can see, one of the problem is what is the ratio of RP and RN, right? So you stop here, right? In internal load capacitance is given. If I say that at this point you can ignore internal load capacitance, then I can go down to individual size of the transistor, because from equivalent size you can distribute them in series parallel, right? So everything you have learned in lecture 4, 5, and 3 need to be basically used to solve this problem. Okay? So, so from lecture 5 now you can basically say I'm not going to add more question other than circuit design. So because we did not cover those things. So any question? And for inverter, spend a lot of time. So three things you have to spend a lot of time. One is MOSFET device structure. Know the structure, know the operation of MOSFET device, both NMOS and PMOS, very clearly. So this midterm will test your knowledge on MOSFET device design and operation. Number 2, inverter. Particularly voltage transfer characteristics. All those points, their definition, VOH, VOL, VM, VIH, VIL, noise margin low, noise margin high, right? Transition width, and all those definitions, very clear. And then number 3 is circuit design. So everything we have discussed today is about circuit design. So step 1 is making this one correct. So there will be 3 sets of questions. I'm giving you the entire midterm exam question. 1 set of questions from MOSFET device, 1 set of questions from inverter, 1 set of questions on circuit design. That's it. Question is out. For the 3rd set, we will start with something that will be like 60% of your exam. For expression, simplify and go down the road, do almost everything we have done here, right? So, because if you go through this practice 1 or 2 times, I'm telling you, you will know everything almost 70-80% about digital circuit design. And that's why the feedback from all my previous students who are working in microelectronic industry, that 90% of the interview questions were covered by first 4 lectures. That's it. To be more specific, lecture 2, 3, and 4. MOSFET device, inverter, and the basics of CMOS circuit design. So if you actually spend a lot of time, and then later, 1 more lecture will be important, that is the memory lecture. There is a unique independent lecture, not related to any one of them. But everything else we are going to discuss in this class, they are all based on 2, 3, and 4. And memory lecture will be developed. So if you want to refresh your knowledge in future, step 1, to go back and look at the material of lecture 2, 3, and 4, and I don't know which is what number I decided for memory lecture. Okay. So next week I will not be here. Don't give hard time to Rahul. He will be conducting the midterm exam and I will be grading you. The question is ready. I'm just going to go over it again one more time. Sometime I will print out the exam most likely tomorrow, and the exam will be with Sharon or Lauren. So you collect those printed exams before the midterm. So midterm will be here in this room. Make sure that students are spread. Friends will be displaced. So
You say it's Tuesday?
eh?
Tuesday?
Next Tuesday, yeah. But as I say, spend a lot of time on these 3 topics. MOSFET device design and operation, inverter operation and design, and the logic circuit design, the step-by-step process we have shown here today.
Will we be having multiple choice questions? Or
No, if there is a multiple choice question, there will be some 1 or 2 multiple choice question, but those questions will be based on your concept here. Yeah.
Lecture 1, do we have to touch upon?
Lecture 1, no. Lecture 1, you can basically just ignore it.
Thank you. So how many?
Because lecture 1 is just storytelling, right? There is nothing substantial in lecture 1. Yes. So I will not burden you with new topics today. Is there any other confusion, any other topic?
Yeah.
Yes, yes.
Question on that, on your circuit here,
Yeah.
you going from like at the top, the Piedmont side, is that fully connected when you got that circle there?
So,
up here, is
oh no,
that
this,
connected all the way
this
across?
one, this one?
Yeah.
No, I just circle it to show that these all nodes are connected to this one node. You don't have to put a circle, just for
Okay,
explaining.
but is that?
That is an internal node capacitance, yes. So, yeah. So this is actually B and C in parallel, connected in series with the block containing A, D, E. And
Okay.
within that block, A is in parallel to D and E.
Gotcha,
D and E are in series. But
gotcha.
we have to be careful where we put D. If I say E is the most active, I have to put E here.
Mhm.
If I say D is most active, then I have to put here. But if
Right.
I say that A is more active, then I have to flip here. I have to put A above, D and E below.
And how do you come to the conclusion that D is most active?
That is the information I will give
You would get that. Okay.
You as the designer, if you know that one of the signal you are using will change more frequently. So that is one of the design technique we have discussed. One of them is put more active signal closer to the output. The other design technique is do not keep more than 4 transistors in series. So we have to divide the complex logic function, logic term, into smaller term. In the given example today we have discussed in class, I included a restriction that you cannot even have 4. It has to be 3 or less. You have to avoid 4 or more series connections. So in your final expression, there, if that condition is repeated in the exam, most likely, that you cannot have any term containing 4 variables. It has to be 3 or less, right? Yes.
In the evaluation, is there a partial marking policy like?
Oh yeah. So let's say if you have stopped here, in this question, it's good. If you have stopped here, BC plus AD plus AE. If you have stopped here, slightly more transistor here. If you have stopped here, you will lose certain point only on question A. But from this expression, if you draw the correct circuit for this, from B and onward, you will not be penalized, because if you stop here, right? But if you draw the correct circuit, addressing all other restriction from here and all those, so yeah, you will be losing point on step 1, but not step 2 and forward. The circuit you have drawn, if you can successfully identify the correct worst case scenario, that will be fine. But this has to be one of the correct answer, right? So that's why there will be a difference. So don't copy your left and right blindly. Use your own understanding to come up with the simplest possible technique. So from the expression, there is a possibility at least 1 or 2 or 3 different versions of answer in step 1 I'm expecting. Because you can say, well, only all of them are 2 inputs. That is the simplest. As you are quickly solving this problem, you may overlook one last step, right? But always, that's why please randomly draw any function. The way I do is, so how actually I come up with this example? I actually wrote this first. BC plus D. And then I just keep adding term, expanding it. So what I want you to do, let's say write a random function, AB plus C. And you just keep expanding it. How do you expand? And then do the reverse order. So write any random function, minimize it, come to the smallest possible expression, and then solve from there. Any other question?
My question is, how do we get the worst case scenario?
For the given circuit,
Yeah.
so once again, for the worst case scenario, first of all, step 1. So I think it's a good question, so let me again repeat. This scenario, how we are going to say. Step 1, identify longest path. For low to high or high to low transition. Step 2, if more than one longest path, right? So identify the longest path. If there are more than one longest path, identify path that injects more capacitance from other side. If any given input combination connects or injects more capacitance, parasitic capacitance from the other side to be charged and discharged, that would be like we have for high to low transition, we had 3 potential candidates, all with length 2. Length means the number of transistors you have to hop on to make a connections from output to the ground or output to the supply. Identify the longest path. If a given circuit has only one longest path, then your problem is very easy. You don't have to worry about it. But in both cases, for this example, in high to low transition, we had 3 potential options. In for low to high, we have 2 potential options, right? So for that, you don't have to write the truth table. Just looking at the circuit, what are the potential combination that gives us the longest path? In case here, I have A, E, B, E, D or C, E, D. These are the 2 with 3 transistors. Between them, we found out that this is not injecting anything from the pull-down network, so we rule that out. This one is adding one more transistor from pull-down network that needs to be charged because this transistor is on. That is my worst case scenario. Okay? Anything else? The 1 hour 15 minutes time is not actually enough for this type of design class. I wish now I am under pressure to finish all the basic topics in this course, but then I don't have the time to discuss different types of design problem in class. Yes.
So we added those internal capacitances to the static CMOS circuit. We added to all the circuits.
Oh yeah. So if the same problem is given for an N-type dynamic circuit, because let's say if I ask you to draw the equivalent circuit for N-type dynamic circuit, so you have to draw this side plus this one. So we have some time. Since you asked, let's quickly see if the same problem, design problem is you need to solve it for an N-type dynamic circuit. It is actually, it's good that you asked. I should not assume. So now, this is VDD. N-type it will be, it's a clock. Here, this side I have and then I have, for the given problem, I have and then I have a clock here, right? This is D, this is E, this is A, this is B, this is C. This is another clock. Now, this one, worst case, TB, HL. Now, what do we do? Recharge is clock equals 0. Evaluation is clock equals 1. We evaluate, we calculate propagation delay and everything when the dynamic circuit is in evaluation phase. In recharge phase, we just recharge into its default value, which is 1. Right? Now, for high to low transition, in the evaluation phase, when clock is 1, right? We only do the calculation in evaluation phase. In recharge phase, we don't do anything. The clock is 1, this is on. This is, so this is off, this is on. Now, TPHL, right? TPHL, if this is on, this side is out of question. So here now, I have potential path will be B, C, and the clock transistor. You have to have a clock transistor in series. Or I can have D, E, and clock transistor. Or I can have E, A, sorry, DA, DA, and the clock. It will be, sorry, DA and clock, DA and clock. Since nothing will be disturbing, so if you solve the problem with any of these three, should be correct. Because in this case, in N-type dynamic circuit, nothing is disturbing you from the upper side, because in evaluation phase clock is 1, then PMOS, this is the PMOS, will be off. But now what will be the equivalent circuit? First we have to draw the internal node capacitance. All these capacitance, including the capacitance for clock, is connected for this node is to the load capacitance. Nothing will change from CMOS. This is the internal node capacitance. There is another internal node capacitance here, right? We have to add one more internal node capacitance here. Because it doesn't matter it's a clock transistor or signal transistor. An additional transistor appeared in series part. So we have to have one internal node capacitance. Because we added that clock transistor, right? So this is the equivalent circuit. So for high to low transition, let's say I pick part BC, right? So from output, I have B, I have C, I have clock to the ground. I have one internal node capacitance here, another internal node capacitance. It is B of M, this is C of M, this is clock of M, right? One internal node, one internal node. So my tau will be, they are more delay model for these three, right? That is my tau M. There is one difference in entire dynamic circuit when it comes to low to high transition. I did not intentionally add that because then you need to basically have a very clear understanding of dynamic circuit operation. We haven't covered that yet. For entire dynamic circuit, TP low to high is 0 by default. Why? Because when I am calculating TP low to high transition, before that calculation, I have to apply a pre-charge phase. Every evaluation phase must be followed by a pre-charge phase. So during the pre-charge, clock is 0 means this is on. This node is already pre-charged to VDD because there is the default value. So when the circuit will produce a binary 1 in entire dynamic circuit. If for a given input combination pull down network is off, there is no connection to the ground, for that input combination output should be 1. So when in the evaluation phase pull down network is off and this clock is, it is off. But in the evaluation phase clock is 0, this is off. But before turning it off, we have already recharged it to VDD during that. So we don't have to do anything. The moment we see that for a given input combination, pull down network is off in the evaluation phase, this node is already recharged to 1. So I have to just read the value. So I don't need to spend any time to charge it to make a 0 to 1 transition. So ideally, TPHL, low to high transition time for a dynamic circuit is always longer than in steady counterpart. Why? Because this additional clock transistor is appearing in the series part. But ideally, low to high transition time of an atomic dynamic circuit is always 0. Because when you are evaluating it, it is already pre-charged to its default value of 1. So in similar case, for P-type dynamic circuit, TP LH low to high will be longer than, will be greater than of P-type dynamic, longer than TP LH of steady. Because there will be a series transistor appearing above the pull-up network for P-type dynamic. But ideally, TPHL for P-type dynamic will be 0 because its default value will be 0. So don't worry about this in return. But if you are given to draw the entire dynamic circuit for a given function and draw the equivalent circuit, you have to make sure that you add this internal node capacitance between the pull down network and this clock transistor. Wherever two transistors or more than transistor they form a node, that node must have an internal node capacitance, right? So that is the difference, but remaining details we will cover later. So at this rate, I'm worried about what I can finish the whole syllabus, but we may have to do some innovative approach. So Rahul, you and I will meet tomorrow in person or over the Zoom to basically discuss our plan for next week. So all the homework and two solutions are uploaded? Okay.
Professor, do we have the solution for this one?
This is the solution we have.
Yeah, but
For the other two?
yeah, for the other.
Third one is a trick question.
Yeah.
That's what we have discussed, right?
Yeah.
But for the second one, let me give you the solution right away. But I can give you in 1 minute.
I can practice, but
But
just
I want you to do.
I will practice, but
Yeah.
just
This one, the first one, the whole lecture is about the first one,
Yeah.
right? But the second one, it will take just 1 minute for me to solve for you. But I want you to solve it. Oh.